This is lecture 20 in BBSP 610. We'll be discussing multiple regression today. In our previous lectures, we've considered univariate regression, meaning that there's a single predictor variable and you're trying to predict an outcome variable. Today we're going to consider the case, say we have more than one predictor variable. A simple example of this, if you remember the amusement park example from a couple lectures earlier, let's say you're going to an amusement park and it costs $10 to get into the park. Every ride you go on costs $3. Say also you buy some hot dogs at the amusement park and each one costs $1.50. In this case, your total cost would be $10 plus $3 times the number of rides plus $1.50 times the number of hot dogs. So you could write this as y equals b0 plus b1 times x1 plus b2 times x2. In this case, x1 would be the number of rides, x2 would be the number of hot dogs, b0 is the admission price, namely $10, b1 is the coefficient or the slope for rides, and b2 is the coefficient for hot dogs. And when you have a multivariable linear function or a multivariable model in general, the way you interpret the slope is that a 1 unit increase in x is associated with a b unit increase or b unit decrease in y if the other x's are held constant. For example, a 1 unit increase in the number of rides is associated with a $3 increase in the total cost if the number of hot dogs is held constant. As you'll recall, in the one variable case, we tried to in the one variable regression case, we chose regression coefficients to minimize the sum of squared errors, that is, the difference between the true values of y and the predicted values of y, using predictions based on a single x. Now we do exactly the same thing in the multivariable case, where we say yi hat equals some linear combination of the x's and try to find the value of b0 hat, b1 hat, etc. that minimizes this sum of squared errors. The formula for calculating this is complicated and ugly. I'm not going to torture you with it. I don't know if you've even had matrix algebra. For the purpose of this class, we'll just let R compute it for us, and then we'll be happy. So an example of multivariable regression, this is another data set that's built into R. And according to the R documentation, it was obtained from 21 days of operation of a plant for the oxidation of ammonia to nitric acid. And the nitric acids produced are absorbed in a countercurrent absorption tower. The response variable in this case is what's known as stack loss, which is the percentage of ingoing ammonia that escapes from the absorption column without being absorbed. So it's an inverse measure of the overall efficiency of the plant. A low stack loss means the plant is functioning very efficiently. High stack loss means the plant is performing poorly. And there's three predictor variables in this model: that airflow, which is the rate of operation of the plant, the water temperature, which is the temperature of the cooling water circulated through the coils in the absorption tower, and acid concentration, which is the concentration of the acid. So to fit this model in R, you use the LM command. It's very similar to the single variable regression. You'll see stack loss is the response variable, and then I say twiddle airflow plus water temp plus acid concentration. In general, the syntax is x1 plus x2 plus x3. I'll give the general syntax here in a second, and you'll see the output below. I'll explain what all these things mean in the output here in a second. Here's an alternative version. It's exactly the same command as I did earlier, but you notice at the top I said LM stack loss twiddle dot rather than airflow plus water temperature plus acid concentration. If you use a dot there, then that makes every single variable in the data frame a possible predictor other than the response variable stack loss. That just saves you some typing. I said in general, LM y twiddle x1 plus x2 will perform multiple regression to predict y based on x1 and x2. If you wanted to add x3, then it would be x1 plus x2 plus x3. And if you want to predict y based on all of the x's, or more generally, if cur data has a column called y that's the response variable, lmy twiddle dot will predict y based on all the other columns of cur data other than y itself. This only works if the data parameter is specified. So for the output for that regression model, you'll see this time the t-tests for each coefficient and the f-test for the overall model are not the same. In fact, maybe I should go back to that real fast. Here's the output. Notice that next to each, there is a p-value for the intercept is in the one variable case. We'll usually ignore that. But you'll also notice there's a p-value for airflow, a p-value for water temperature, and a p-value for acid concentration. Airflow, we have a p-value of about 5.8 times 10 to the minus 5. Water temperature, it's about 0.003. Acid concentration, it's about 0.34. And then the F statistic down at the bottom is about 3 times 10 to the minus 9. So the p-value corresponding to airflow, which is the t-statistic, that's the p-value for testing the null hypothesis that the coefficient for airflow is different from 0. So 5.8 times 10 to the minus 5, very strong evidence against the null hypothesis. We conclude that airflow has a positive coefficient and that higher airflow is associated with greater stack loss. Similarly, the p-value for water temperature isn't quite as strongly significant, but it's still strong enough that you would reject the null hypothesis that it's 0 under any reasonable criteria. Conclude that a higher water temperature is associated with greater stack loss. Acid concentration, however, with a p-value of 0.34, we fail to reject the null hypothesis that that coefficient is equal to 0. So in general, a t-test for a given coefficient tests the null hypothesis that the particular coefficient is 0. The f-test tests the null hypothesis that all of the coefficients simultaneously are 0. I guess I forgot to discuss that when we were looking at the stack loss data, but the p-value on the order of 10 to the minus 9 is for testing the null hypothesis that all three coefficients for airflow, water temperature, and acid concentration are all 0 simultaneously. With the p-value on the order of 10 to the minus 9, there's very strong evidence against that null hypothesis. In the one variable case, the t-test and the f-test will give exactly the same results, which makes sense because there's only one variable. The t-test tests the null hypothesis that one variable is equal to 0. The f-test tests the null hypothesis that all the variables are equal to 0. In this case, there's only one variable, so it's testing exactly the same hypothesis. But when you do multiple regression, there will be more than one predictor variable, so more than one t-statistic, and in general, the f-statistic will be different from these t-statistics. And so fitting a multiple regression model is easy enough. Interpreting a multiple regression model is much harder, and it's easy to make mistakes. And I'm going to spend most of the rest of this lecture describing things that can go wrong and all the things that you need to be careful with when interpreting a multiple regression model. In particular, the p-values and even the signs, the coefficients, can sometimes be misleading, so you have to be very careful when you interpret these multiple regression models and know what everything means. So let's look at the stack loss data again. We've looked at this for the last couple slides. Note that the t-statistic for airflow is strongly significant. The t-statistic for water temperature is significant, although not as strong as it was for airflow. And for acid concentration, we fail to reject the null hypothesis of no difference between that the coefficient for acid concentration is 0. Now let's look at these one at a time. If we look at airflow by itself, we get a larger coefficient, a stronger p-value, but the basic conclusion doesn't change, that airflow is a very strong predictor of stack loss. But when we look at water temperature, it's a little interesting. Water temperature by itself, if you look at the p-value and the r-squared, it's almost as good as airflow. Suddenly the p-value is 2 times 10 to the minus 7 rather than just 0.003 or whatever it was in the multivariable case. And acid concentration is almost statistically significant, and the sign of the coefficients reversed. In the multivariable model, it looked like higher acid concentration was associated with lower stack loss, but now this is showing higher acid concentration is associated with greater stack loss. So what does all this mean? It looks like the best way to interpret this is airflow and water temperature both strongly associated with stack loss. If you combine the two variables, you just get only a little more information than you do from airflow by itself. I make that conclusion based on a number of things. That here note that the r-squared for the multivariable model is 89.8, so we're explaining about 90% of the variation in stack loss based on these three variables. But airflow by itself gives us 0.837, or 0.838 rather, which is not that much different from the multivariable model. And even airflow, or even water temperature by itself, is giving us an r-square of 0.75, which isn't that bad. So all this suggests to me that if you combine both airflow and water temperature, you get a little more information than from airflow alone, but not that much. An acid concentration, best case scenario, it's weakly associated with stack loss, and it definitely doesn't tell us anything more than what we get from airflow and water temperature by themselves. And we saw in these previous slides that the sign of the acid concentration variable reversed itself between the multivariable model and the univariate model. And this is actually quite common for this coefficient to change, so you don't want to rely on the sign of a multivariable regression coefficient to tell you the direction of an association. And so you have to be careful when you build these multivariable models. The variables that you include in a multiple regression model can have a big effect on the final form of the model. So you have to choose which variables to include carefully. If you don't include the correct variables, you can get a biased model. An example of this I discussed it a bit in a previous lecture, but just for review in a bit more detail. In World War II, the military used a regression model to predict the results of bombing runs during the war. And if the plane was flying slower at a lower elevation, that was associated with increased probability of success. Okay, fine, makes sense. But if there were lots of enemy fighters in the air trying to shoot your bomber down, that was associated with higher probability of success, which seems weird. Well, what was going on here is the military had left an important confounding variable in the model, cloud cover. If it's a cloudy day, then the enemy won't be trying to shoot you down, but you can't see your target, so you have a hard time hitting it. So if you omit a relevant variable, it can make your coefficient estimates and corresponding t-tests and confidence intervals completely meaningless. Another example that I encountered in my personal research is we did a study to discover risk factors for temporomandibular disorder, and we expected that patients with TMD would show heightened sensitivity to pain generally. So we put a thermal probe on their arm, heated it up to a certain temperature once every 3 seconds, then turned it off, and then turned it on again after a 1-second rest period. Repeated this for a total of 30 seconds. Each administered a total of 10 pulses. Each pulse we gave a pain rating on a scale. We asked the participants to give pain rating on a scale from 0 to 100. And we summarized these into two predictor variables, namely their pain rating at the first pulse and the rate at which the rating increased. And when we did regression on each variable one at a time, we found that the initial rating was associated with TMD, but the rate of increase was not. But we included both the variables in the model. They were both very strongly significant. So what's going on there? In this case, there's two ways that a patient can have an elevated risk of TMD. They can have a high initial pain rating, or they can have a low initial pain rating that increases quickly. So if, and the first group was much more common than the second group, so if we just looked at the rate of increase, many of the people who had a high initial pain rating had a low rate of increase because they were high to begin with. So we didn't see that association. We included both variables in the model, then we saw the association. This is what's known as an interaction. So sometimes a variable that looks like it's not significant by itself can become significant when you include it with another variable in the model. And if you include an irrelevant variable in the model, then it will increase the variance of the model, and this will give you wider confidence intervals for your estimates and more conservative p-values. This may not be a major problem if you have enough data, but in general you want to try to exclude irrelevant variables whenever you can. So how do you know if a variable is relevant? Well, the best way to do this is the results on this slide. Say we want to know if x0 increases your ability to predict y after considering all the other x's. So the first thing you do is you regress y on all of the x's except for x0. Then you regress x0 on all of the x's except for x0. And then you regress the residuals from the first regression on the residuals from the second regression. If there's statistically significant association between these residuals, then we conclude that x0 adds additional information to the model. That's the way you should do this. In practice, nobody does it that way. Usually what you do is you just do two multiple regression models, one that includes x0 and one that does not, and you see if the coefficient for x0 is significantly different from 0 in this new model. It's not as reliable, but it's easier to do, and the vast majority of the time it gives you the same results, and journals let you get away with that all the time, so whatever. It is important to note, however, that you can't use r² to determine if a variable adds additional information, because r² will always increase when you add more variables to a model. So does this mean that we should just include every variable that's relevant and get rid of variables that don't seem to be associated with the model? Well, unfortunately, that still doesn't necessarily give you the best possible result because of a problem known as multicollinearity. That if x's are highly correlated with one another, you add new x's into the model, gives you almost no additional information. We saw this to a degree in the stack loss data. By itself, water temperature tells you quite a bit about stack loss, but if you already know airflow, water temperature doesn't give you that much more information beyond what you get from airflow. And once you add additional variables to the model, you'll increase the variance of the model and make your model less accurate, even if every single individual x that you add to the model is strongly correlated with y. For example, this is a famous data set where this sort of thing can cause problems for you. It's called Longley and it's built into R. The objective of this data set was to predict the number of people employed based on various things known to affect employment, GDP, population, etc. And all the predictors in these models are ridiculously highly correlated with one another that can make the model difficult to predict. So here's the R output when we fit this model. I just say summary LM employed twiddle dot. The data is the Longley data. And end up with some variables significant and some not, include the populations not significant or GNP, which already should raise eyebrows. How is, when GDP is higher, when more people have jobs, why is that not associated with employment? Is the number of people in the armed forces really going to be a better predictor of how many people have jobs than GDP? If you look at the pairwise scatterplots of this data, you can start to see what's going on here, that almost every one of these variables is very strongly correlated with the others. In fact, some, like the population between year and population, for instance, or GNP and GNP deflator, are almost perfectly linear. Quick little R note, to produce a plot like I just produced, you can use the pairs command in R. It'll plot pairwise scatterplots for each possible pair of variables. So multicollinearity means you don't want to just simply mindlessly add every relevant variable to a regression model. In general, finding the optimal set of variables to give you optimal predictions is hard, and it's actually an active research area that keeps people like me employed. I'm not going to expect you to know all this stuff for this class. Just the main thing I want you to know is to interpret this regression output critically. In fact, right now, I'm going to tell you the single most common mistake that people make in this class when interpreting these models. Let's go back to the Longley data again, and let's, rather than fitting a multivariable model including all these possible predictors, let's only include GNP as a predictor. In this case, suddenly GNP is very strongly significant. We have an R squared of like 0.97, almost perfect predictive accuracy, despite the fact that it was not significant in the multivariable model and gave us a t statistic that was very strongly not significant. We see GNP wasn't associated with employment in the multivariable model, but it was strongly associated with in the univariable model. So you do not want to rely on multivariable models to tell you if X and Y are associated. You should do the univariate model first and then do multivariate models to look for interactions and things like that. Every single year that I've taught this class, when I used to give a final, people would make that mistake. I would say which of these list of variables is associated with Y. They would plug them all into a multivariable model, and anything that had a coefficient significantly different from 0, they would say was associated with Y. That is not correct. In this class, you won't have a final, but you will have homeworks and a final project. Please do not make that mistake. So the things to remember for today's lecture is you can generalize regression to cases where there's multiple predictor variables, and you need to use caution when interpreting the output of multivariable models. In particular, you don't want to rely on multivariable models to tell you if there's an association between an individual X and Y. You should use univariate models for that. Deciding which variables to include in such a model turns out to be a hard problem. R commands, you say lmy twiddle x1 plus x2. That'll fit a multivariable regression model to predict y based on multiple variables. Say y twiddle dot, that'll use all the columns of the data set as predictors, and you can use pairs to produce pairwise scatterplots.